Thomas de Colmar simplified his arithmometer by removing the one-digit multiplier / divider. This made it a simple adding machine, but thanks to its moving carriage used as an indexed accumulator, it still allowed for easy multiplication and division under operator control. The arithmometer was now adapted to the manufacturing capabilities of the time. Thomas could therefore manufacture consistently a sturdy and reliable machine. Manuals were printed and each machine was given a serial number. Its commercialization launched the mechanical calculator industry. Banks, insurance companies, government offices started to use the arithmometer in their day-to-day operations, slowly bringing mechanical desktop calculators into the office. In 1878 Burckhardt, of Germany, was the first to manufacture a clone of Thomas' arithmometer. Until then Thomas de Colmar had been the only manufacturer of desktop mechanical calculators in the world, and he had manufactured about 1,500 machines. Eventually 20 European companies will manufacture clones of Thomas' arithmometer until World War II. Theodor E. Felt, in the US, patented the comptometer in 1886. It was the first successful key-driven adding and calculating machine. Key-driven refers to the fact that just pressing the keys causes the result to be calculated, no separate lever or crank has to be operated. Other machines are sometimes called keyset. In 1887, he joined with Robert Tarrant to form the Felt and Tarrant Manufacturing Company. The comptometer type calculator was the first machine to receive an all-electronic calculator engine in 1961, the Anita Mark VII released by Sumlock Comptometer of the UK. In 1890 W.T. Ardner got the rights to manufacture his calculator back from Königsberger & C., which had held them since it was first patented in 1878, but had not really produced anything. Ardner used his St. Petersburg workshop to manufacture his calculator, and he built and sold 500 machines in 1890. This manufacturing operation shut down definitively in 1918 with 23,000 machines produced. The Ardner arithmometer was a redesigned version of the arithmometer of Thomas de Colmar with a pinwheel engine, which made it cheaper to manufacture and gave it a smaller footprint while keeping the advantage of having the same user interface. In 1892 Ardner sold the Berlin branch of his factory, which he had opened a year earlier, to Grimm, Natalis and Company. They moved the factory to Braunschweig and sold their machines under the brand name of Brunsviga. Brunsviga is the Latin name of the town of Braunschweig. This was the first of many companies which would sell and manufacture clones of Ardner's machine all over the world. Eventually millions were sold well into the 1970s. In 1892, William S. Burroughs began commercial manufacture of his printing adding calculator. Burroughs Corporation became one of the leading companies in the accounting machine and computer businesses. The millionaire calculator was introduced in 1893. It allowed direct multiplication by any digit, one turn of the crank for each figure in the multiplier. It contained a mechanical product lookup table, providing units and tens digits by differing lengths of posts. Another direct multiplier was part of the Moon-Hopkins billing machine. That company was acquired by Burroughs in the early 20th century. Automatic mechanical calculators, edit. In 1822, Charles Babbage presented a small cogwheel assembly that demonstrated the operation of his difference engine, a mechanical calculator which would be capable of holding and manipulating 7 numbers of 31 decimal digits each. It was the first time that a calculating machine could work automatically using as input results from its previous operations. It was the first calculating machine to use a printer. The development of this machine, later called difference engine number 1, stopped around 1834. 2. In 1847, Babbage began work on an improved difference engine design, his difference engine number 2. None of these designs were completely built by Babbage. In 1991, the London Science Museum followed Babbage's plans to build a working difference engine number 2 using the technology and materials available in the 19th century. 3. In 1855, Georg Schiutz completed a working difference engine based on Babbage's design. The machine was the size of a piano, and was demonstrated at the Exposition Universelle in Paris in 1855. It was used to create tables of logarithms. 4. In 1875, Martin Wiberg redesigned the Babbage /Schiutz difference engine and built a version that was the size of a sewing machine. Programmable mechanical calculators, edit. Minimal but working demonstration part of the mill from the analytical engine, finished by Babbage's son around 1906. 1. In 1834, Babbage started to design his analytical engine, which will become the undisputed ancestor of the modern mainframe computer with 2 separate input streams for data and program, a primitive Harvard architecture, printers for outputting results, 3 different kind, processing unit, mill, memory, store, and the first ever set of programming instructions. In the proposal that Howard Aiken gave IBM in 1937 while requesting funding for the Harvard Mark I, which became IBM's entry machine in the computer industry, we can read, few calculating machines have been designed strictly for application to scientific investigations, the notable exceptions being those of Charles Babbage and others who followed him. In 1812, Babbage conceived the idea of a calculating machine of a higher type than those previously constructed to be used for calculating and printing tables of mathematical functions. After abandoning the difference engine, Babbage devoted his energy to the design and construction of an analytical engine of far higher powers than the difference engine. 2. In 1843, during the translation of a French article on the analytical engine, Ada Lovelace wrote, in one of the many notes she included, an algorithm to compute the Bernoulli numbers. This is considered the first computer program. 3. From 1872 until 1910, Henry Babbage worked intermittently on creating the mill, the central processing unit of his father's machine. After a few setbacks, he gave in 1906 a successful demonstration of the mill which printed the first 44 multiples of pi with 29 places of figures. Cash registers, edit. Further information, cash registers. The cash register, invented by the American saloon keeper James Ritty in 1879, addressed the old problems of disorganization and dishonesty in business transactions. It was a pure adding machine coupled with a printer, a bell and a 2-sided display that showed the paying party and the store owner, if he wanted to, the amount of money exchanged for the current transaction. The cash register was easy to use and, unlike genuine mechanical calculators, was needed and quickly adopted by a great number of businesses. 84 companies sold cash registers between 1888 and 1895, only 3 survived for any length of time. In 1890, 6 years after John Patterson started NCR Corporation, 20,000 machines had been sold by his company alone against a total of roughly 3,500 for all genuine calculators combined. By 1900, NCR had built 200,000 cash registers and there were more companies manufacturing them, compared to the Thomas /Pay an Arithmometer company that had just sold around 3,300 and Burroughs had only sold 1,400 machines. Prototypes and limited runs, edit. 1. In 1820, Thomas de Colmar patented the arithmometer. It was a true 4-operation machine with a 1-digit multiplier /divider, The millionaire calculator released 70 years later had a similar user interface. He spent the next 30 years and 300,000 francs developing his machine. This design was replaced in 1851 by the simplified arithmometer, which was only an adding machine. 2 from 1840, Didier Roth patented and built a few calculating machines, one of which was a direct descendant of Pascal's calculator. 3 in 1842, Timoleon Morel invented the arithmoral, based on the arithmometer, which could multiply two numbers by simply entering their values into the machine. 4 in 1845, Israel Abraham Staffel first exhibited a machine that was able to add, subtract, divide, multiply and obtain a square root. 5 around 1854, André Michel Guéry invented the ordonnateur statistique, a cylindrical device designed to aid in summarizing the relations among data on moral variables, crime, suicide, etc. 6 in 1872, Frank S. Baldwin in the U.S. invented a pinwheel calculator. 7 in 1877, George B. Grant of Boston in the United States began producing the Grant mechanical calculating machine capable of addition, subtraction, multiplication and division. The machine measured 13 x 5 x 7 inches and contained 80 working pieces made of brass and tempered steel. It was first introduced to the public at the 1876 Centennial Exposition in Philadelphia. 8 in 1883, Edmondson of the United Kingdom patented a circular step drum calculator. Grant's barrel, 1877. 1900s to 1970s, edit. Further information, History of computing hardware. Mechanical calculators reach their zenith, edit. Two different classes of mechanisms had become established by this time, reciprocating and rotary. The former type of mechanism was operated typically by a limited travel hand crank. Some internal detailed operations took place on the pull, and others on the release part of a complete cycle. The illustrated 1914 machine is this type. The crank is vertical, on its right side. Later on, some of these mechanisms were operated by electric motors and reduction bearing that operated a crank and connecting rod to convert rotary motion to reciprocating. The latter type, rotary, had at least one main shaft that made one, or more, continuous revolution, one addition or subtraction per turn. Numerous designs, notably European calculators, had hand cranks, and locks to ensure that the cranks were returned to exact positions once a turn was complete. The first half of the 20th century saw the gradual development of the mechanical calculator mechanism. The Dalton adding listing machine introduced in 1902 was the first of its type to use only 10 keys, and became the first of many different models of 10-key add listers manufactured by many companies. In 1948 the cylindrical Curter calculator, which was compact enough to be held in one hand, was introduced after being developed by Kurt Herz-Stark in 1938. This was an extreme development of the stepped gear calculating mechanism. It subtracted by adding complements. Between the teeth for addition were teeth for subtraction. From the early 1900s through the 1960s, mechanical calculators dominated the desktop computing market. Major suppliers in the USA included Friden, Monroe, and SCM/Marchant. These devices were motor-driven, and had movable carriages where results of calculations were displayed by dials. Nearly all keyboards were full. Each digit that could be entered had its own column of 9 keys, 1 plus a column clear key, permitting entry of several digits at once. See the illustration below of a Marchant figmatic. One could call this parallel entry, by way of contrast with 10-key serial entry that was commonplace in mechanical adding machines. and is now universal in electronic calculators. Nearly all Friden calculators, as well as some rotary, German, dials had a 10-key auxiliary keyboard for entering the multiplier when doing multiplication. 4 keyboards generally had 10 columns, although some lower-cost machines had 8. Most machines made by the 3 companies mentioned did not print their results, although other companies, such as Olivetti, did make printing calculators. In these machines, addition and subtraction were performed in a single operation, as on a conventional adding machine, but multiplication and division were accomplished by repeated mechanical additions and subtractions. Friden made a calculator that also provided square roots, basically by doing division, but with added mechanism that automatically increment the number in the keyboard in a systematic fashion. The last of the mechanical calculators were likely to have shortcut multiplication, and some 10-key, serial entry types had decimal point keys. However, decimal point keys required significant internal added complexity, and were offered only in the last designs to be made. Handheld mechanical calculators such as the 1948 Curta continued to be used until they were displaced by electronic calculators in the 1970s. Typical European 4-operation machines use the Agner mechanism, or variations of it. This kind of machine included the original Agner, Brunsviga and several following imitators, starting from Triumphator, Thales, Walther, Facit up to Toshiba. Although most of these were operated by hand cranks, there were motor-driven versions. Harman calculators externally resembled pinwheel machines, but the setting lever positioned a cam that disengaged a drive pull when the dial had moved far enough. Although Dalton introduced in 1902 first 10-key printing adding, 2 operations, the other being subtraction, machine, these features were not present in computing, 4 operations, machines for many decades. Facit T, 1932, was the first 10-key computing machine sold in large numbers. Olivetti Divisuma 14, 1948, was the first computing machine with both printer and a 10-key keyboard. 4 keyboard machines, including motor-driven ones, were also built until the 1960s. Among the major manufacturers were Mercedes Euclid, Archimedes, and Madders in Europe. In the USA, Friden, Marchant, and Monroe were the principal makers of rotary calculators with carriages. Reciprocating calculators, most of which were adding machines, many with integral printers, were made by Remington Rand and Burroughs, among others. All of these were key-set. Felt and Tarrant made comptometers, as well as Victor, which were key-driven. The basic mechanism of the Friden and Monroe was a modified Leibniz wheel, better known, perhaps informally, in the USA as a stepped drum or stepped reckoner. The Friden had an elementary reversing drive between the body of the machine and the accumulator dials, so its main shaft always rotated in the same direction. The Swiss Madders was similar. The Monroe, however, reversed direction of its main shaft to subtract. The earliest Marchants were pinwheel machines, but most of them were remarkably sophisticated rotary types. They ran at 1,300 addition cycles per minute if the plus bar is held down. Others were limited to 600 cycles per minute. Because their accumulator dials started and stopped for every cycle, Marchant dials moved at a steady and proportional speed for continuing cycles. Most Marchants had a row of 9 keys on the extreme right, as shown in the photo of the Figmatic. These simply made the machine add for the number of cycles corresponding to the number on the key, and then shifted the carriage one place. Even 9 add cycles took only a short time. In a Marchant, near the beginning of a cycle, the accumulator dials moved downward into the dip, away from the openings in the cover. They engaged drive gears in the body of the machine, which rotated them at speeds proportional to the digit being fed to them, with added movement, reduced 10-1, from carries created by dials to their right. At the completion of the cycle, the dials would be misaligned like the pointers in a traditional watt-hour meter. However, as they came up out of the dip, a constant lead disc cam realigned them by way of a limited travel spur gear differential. As well, carries for lower orders were added in by another planetary differential. The machine shown has 39 differentials in its 20-digit accumulator. In any mechanical calculator, in effect, a gear sector or some similar device moves the accumulator by the number of gear teeth that corresponds to the digit being added or subtracted. 3 teeth changes the position by a count of 3. The great majority of basic calculator mechanisms move the accumulator by starting, then moving at a constant speed, and stopping. In particular, stopping is critical, because to obtain fast operation, the accumulator needs to move quickly. Variants of Geneva drives typically block overshoot, which, of course, would create wrong results. However, 2 different basic mechanisms, the Mercedes Euclid and the Marchant, move the dials at speeds corresponding to the digit being added or subtracted. A1 moves the accumulator the slowest, and A9 the fastest. In the Mercedes Euclid, a long slotted lever, pivoted at one end, moves 9 racks, straight gears, endwise by distances proportional to their distance from the lever's pivot. Each rack has a drive pin that is moved by the slot. The rack 1 is closest to the pivot, of course. For each keyboard digit, a sliding selector gear, much like that in the Leibniz wheel, engages the rack that corresponds to the digit entered. Of course, the accumulator changes either on the forward or reverse stroke, but not both. This mechanism is notably simple and relatively easy to manufacture. The Marchant, however, has, for every one of its 10 columns of keys, a 9-ratio pre-selector transmission with its output spur gear at the top of the machine's body, that gear engages the accumulator gearing. When one tries to work out the numbers of teeth in such a transmission, a straightforward approach leads one to consider a mechanism like that in mechanical gasoline pump registers, used to indicate the total price. However, this mechanism is seriously bulky, and utterly impractical for a calculator. 90-tooth gears are likely to be found in the gas pump. Practical gears in the computing parts of a calculator cannot have 90 teeth. They would be either too big, or too delicate. Given that 9 ratios per column implies significant complexity, a Marchant contains a few hundred individual gears in all, many in its accumulator. Basically, the accumulator dial has to rotate 36 degrees, 1/10 of a turn, for 1, and 324 degrees, 9/10 of a turn, for 9, not allowing for incoming carries. At some point in the gearing, 1 tooth needs to pass for a 1, and 9 teeth for a 9. There is no way to develop the needed movement from a drive shaft that rotates 1 revolution per cycle with few gears having practical, relatively small, numbers of teeth. The Marchant, therefore, has 3 drive shafts to feed the little transmissions. For 1 cycle, they rotate a half, a quarter, and 1 forward/12 of a revolution. 1. The 1 forward/2 turn shaft carries, for each column, gears with 12, 14, 16, and 18 teeth, corresponding to digits 6, 7, 8, and 9. The 1 forward/4 turn shaft carries, also, each column, gears with 12, 16, and 20 teeth, for 3, 4, and 5. Digits 1 and 2 are handled by 12 and 24 tooth gears on the 1 forward/12 revolution shaft. Practical design places the 12th thread shaft more distant, so the 1/4/4 turn shaft carries freely rotating 24 and 12 tooth idler gears. For subtraction, the drive shaft's reversed direction. In the early part of the cycle, one of 5 pendants moves off center to engage the appropriate drive gear for the selected digit. Some machines had as many as 20 columns in their full keyboards. The monster in this field was the duodecillion made by Burroughs for exhibit purposes. For sterling currency, £/s/d, and even farthings, there were variations of the basic mechanisms, in particular with different numbers of gear teeth and accumulator dial positions. To accommodate shillings and pence, extra columns were added for the tens digit, s, 10 and 24 shillings, and 10 for pence. Of course, these functioned as radix 20 and radix 12 mechanisms. A variant of the marchant, called the binary octal marchant, was a radix 8, octal, machine. It was sold to check very early vacuum tube, valve, binary computers for accuracy. Back then, the mechanical calculator was much more reliable than a tube/valve computer. As well, there was a twin marchant, comprising 2 pinwheel marchants with a common drive crank and reversing gearbox. Twin machines were relatively rare, and apparently were used for surveying calculations. At least one triple machine was made. The facet calculator, and one similar to it, are basically pinwheel machines, but the array of pinwheels moves sidewise, instead of the carriage. The pinwheels are biquinary. Digits 1 through 4 cause the corresponding number of sliding pins to extend from the surface. Digits 5 through 9 also extend a 5-tooth sector as well as the same pins for 6 through 9. The keys operate cams that operate a swinging lever to first unlock the pin positioning cam that is part of the pinwheel mechanism. Further movement of the lever, by an amount determined by the keys cam, rotates the pin positioning cam to extend the necessary number of pins. Stylus-operated adders with circular slots for the stylus, and side-by-side wheels, as made by Sterling Plastics, USA, had an ingenious anti-overshoot mechanism to ensure accurate carries. The end of an era, edit. Mechanical calculators continued to be sold, though in rapidly decreasing numbers, into the early 1970s, with many of the manufacturers closing down or being taken over. Comptometer-type calculators were often retained for much longer to be used for adding and listing duties, especially in accounting, since a trained and skilled operator could enter all the digits of a number in one movement of the hands on a comptometer quicker than was possible serially with a 10-key electronic calculator. In fact, it was quicker to enter larger digits in 2 strokes using only the lower numbered keys. For instance, a 9 would be entered as 4 followed by 5. Some key-driven calculators had keys for every column, but only 1 through 5. They were correspondingly compact. The spread of the computer rather than the simple electronic calculator put an end to the comptometer. Also, by the end of the 1970s, the slide rule had become obsolete. See also, edit. 1 abacus. 2 adding machine. 3 calculator. 4 history of computing hardware. 5 mechanical computer. 6 tabulating machine. 7 George Brown, inventor. Notes, edit.